All right, so let's talk a little bit about microcontrollers. So a microcontroller is basically just a small computing device that has a CPU, some code memory, a small amount of RAM, and some digital I/O pins. And microcontrollers are incredibly useful for a wide variety of embedded applications. Just about any kind of application you can think of where you would build a small computing device into a system is something where a microcontroller might be a good solution. The one application that I'm interested in is using the microcontroller as a keyboard controller. So basically I want the microcontroller to scan the key matrix of a keyboard, decode which keys are pressed and released, and then send appropriate scan codes to the host system. So that'll be the basis for adding a keyboard to our 8-bit system eventually. That's where this ties in to the 8-bit computer project. So there have been all kinds of microcontrollers over the years. Some early examples are the Intel 8048 and the Intel 8051. Here are a couple examples of those. They were extraordinarily popular, and in fact the 8051 microcontrollers are still in production from a variety of manufacturers and are still fairly widely used. However, there are all kinds of more modern microcontrollers, such as some of the modern 8-bit ones. The AVR series is very popular. These, of course, were famously the basis for Arduinos, the first Arduino devices. So here is a standalone AT-Mega 328 microcontroller. Here is an Arduino Nano, which includes basically that same chip, but as an Arduino. And then there are, of course, all kinds of modern microcontroller chips, mostly based on the ARM architecture, such as the very popular STM32 microcontrollers. And there are all kinds of hobbyist-friendly examples of systems built on these 32-bit ARM microcontrollers, such as the TC3 and the ubiquitous Blue Pill devices. And, all of these sort of modern ones are great for hobbyists. They're easy to use. So why am I interested in the 8051? And the answer is quite simply, all of these modern ones are just too easy. And they're not authentic in the sense that, in the 80s, which is kind of the era I'm trying to capture in this 8-bit project, you would have developed your firmware code for your embedded application using one of these simple classic controllers like the 8048 or the 8051. So, for example, the original IBM PC keyboard used an Intel 8048. The IBM AT keyboard used an 8042, both of which are part of the 8048 family. So that's really what I want to capture in my project. And the AVR and Arduino chips would simply be too easy to use. And I have this kind of crazy idea that I actually have this thing, which is an Intel 87C51, which is an EEPROM programmable version of the 8051. And so if I can develop my firmware, keyboard controller firmware using 8051 code, I'm hoping I can actually burn it into this device. And this is absolutely an authentic device for the period. Looking at the date code on this one, looks like 1988. So, no, 1980. Yeah, so that thing's old. Cool. All right, so let's talk about 8051 family microcontroller parts, and this is by no means a comprehensive guide. I'm just trying to give you a sense of some of the parts that are available and how they are related to each other. So the original ones are the 8051 and 8052. These are similar. They vary a little bit in the amount of RAM and the amount of ROM that they have. The ROM in these devices that is built in is a mask ROM, meaning in order to get the ROM in there, you have to send your firmware program to the manufacturer, and it is actually sort of programmed at the factory. Clearly not an option for hobbyists. So the nice thing about these parts is that there are actually a total of 32 GPIO pins, which is quite a bit. You can do a lot of control and sensing using 32 pins. The 8031 and 8032 are essentially variations of 8051 and 8052 where there is no mask ROM, and so in order to run code out of these devices, you need an external ROM. One thing to note is that you can use 8051 and 8052 devices with an external ROM. There's basically a pin that you can use to disable the internal mask ROM and then treat them as 8031 and 8032 devices. However, in order to use the external ROM, it takes away 16 of your GPIO pins because they need to be used as essentially address and data lines, and which it kind of is not so great if you're planning to actually use all 32 GPIO pins, or certainly if you're planning to use more than 16, that's a problem. The 80, C31, C32, C51, C52, these are CMOS variants of the original 8051 family devices. I showed a moment ago the 87C51 device, which is basically an 8051 with EEPROM, UV erasable EEPROM program memory on it, and so these are the devices that you would have used sort of back in the day to prototype your system. You develop your firmware, burn it into the EEPROM on your 87C51 or 87C52 device, test it in your application, use a UV eraser to erase the code memory before you programmed it again, and then when your firmware program was done, you would send the firmware image off to the factory, and it would be burned into the mask ROM on an actual 8051 or 8052. That's kind of the old school method of product development using these devices. But of course, since then, flash memory is now a thing, and so a lot of manufacturers, predominantly Atmel, I think was one of the early players, added flash memory to these 8051 family parts. And so Atmel has, for example, the 89C51 and 89C52 devices. These are basically very much like the 8051 and 8052, but they have flash memory, which is great because you can just pop it into the programmer, and the programmer can both erase and program your firmware into the device sort of all in one step. It's a lot faster than having to use a UV eraser. And Atmel also created a lot of variations, including the 89C2051, with sort of reduced numbers of pins for kind of smaller applications. And so the one I'll show in the video today is the 89C2051, which has 20 pins, and 15 of which can be used as GPIO pins. So that's pretty pretty respectable. You can do a lot with with that amount of I/O. So here is my plan. My plan is I'm going to use my 89C2051 parts basically to learn about how the 8051 architecture works and what the programming model is and how to develop applications, using the 8051 family. I have ordered some 89C52 parts, and those are the ones I'm going to use for sort of my official firmware development for the keyboard controller. And then, assuming I reach success in the keyboard controller firmware, I am hoping I can take my firmware program and burn it into an 87C51 device, one of my EEPROM programmable devices, and that will become the production chip, and that will allow me to essentially have a vintage, period authentic keyboard controller part in my 8-bit system. All right, so here are the requirements, the things we're going to need for our experiments with the AT89C2051 microcontroller. For our programming software, we're going to use the SDCC C compiler. That stands for the Small Device C compiler. I just installed it from the Ubuntu package repositories. The one that was in there worked fine. I'm going to use my MiniPro TL866A programmer with the Windows software running under Wine to basically program the device. And for the actual sort of hardware prototyping, I soldered some header pins to a ZIF socket, so that way I can easily insert and remove the microcontroller from the circuit. And the 8051 devices need an external crystal, so I'm using a 16 megahertz crystal and two 22 picofarad capacitors for the clock frequency on the microcontroller. We also need a 100 nanofarad capacitor basically to generate reset for the microcontroller, and then the other usual prototyping stuff, breadboard, LEDs, resistors, stuff like that. And everything I'm going to show is basically based on an Instructable by Piotr Bakalarski, and I will put a link to that Instructable in the video description. He also describes how to make a Arduino-based programmer for the device. I'm just going to use my MiniPro. All right, so here is the pinout for the 89C2051, and it's pretty standard, I would say, if you've used microcontrollers before. There's a ground and VCC inputs. Those are the power inputs. Pin 1 is the reset pin. It's active high, so if you send high voltage on that pin, it resets the microcontroller. XTAL1 and XTAL2, these are the inputs for the crystal oscillator, and we'll see that in the schematic in a moment. And basically all the other pins are for either GPIO or special functions exposed as 2 ports, port 1 and port 3. There are in fact 4 ports in the architecture, including port 0 and port 2, but because this is a reduced pin count device, it only has external pins for 2 of the 4 ports. Okay, let's look at the schematic. All right, so here is the schematic for our first experiment. We're going to blink an LED that is connected to pin 1.3, so pin 3 of port 1. And I take no credit for the schematic. This is Piotr Bakalarski's demo circuit, and I really am grateful that he posted that, and it was a really excellent starting point for me. Basically, anytime you're learning a new microcontroller, if you can write a program and build a circuit so that you can blink an LED under software control, that pretty much gives you a starting point for building more complex applications. And so if you can get that to work, you're probably on your way to getting more interesting things to work as well. So basically, there's not a whole lot to talk about in the circuit. You know, we obviously hook up the power inputs to ground and VCC, the 2 crystal oscillator inputs. We're going to use a 16 megahertz crystal, and then we have 22 picofarad capacitors to ground. That's a pretty standard arrangement for crystal oscillators. Pin 1, the reset pin, actually has a bit of an interesting component attached to it, which is this capacitor. And the idea is when the system is powered on, as the capacitor charges, the voltage on this node of the circuit will decrease and essentially start high but then fall towards ground. So that's essentially how we're generating our reset signal when the system starts up. So you definitely need this capacitor. And then the LED is connected to VCC through a current limiting resistor. And basically when a low voltage is applied here on this output pin, current will flow from VCC through the resistor and the LED into the output pin. So interestingly, on the 8051, the output pins, they can sink current to ground, but they cannot source current. So we could not have hooked up this LED to power its, to have a high voltage at its anode. Basically, only a tiny amount of current can actually be supplied on the output pin when the logic level is high, but we can, when the output level is low, we can basically sink, a reasonably large amount of current, certainly enough to light up this LED. All right, so here is the test program that accompanies the LED blink circuit. And once again, this is Piotr Bakalarski's work, not mine. I'm very appreciative that he posted such a nice, clean example application. I really learned a lot from it. So basically what this program is doing is that there's 2 global variables, LED state and timer counter. LED state is going to be either 0 or 1. That is going to control whether the LED is on or off. This timer counter variable, it starts at a particular initial value, and then every time a timer interrupt occurs, counts down. When when this counter variable reaches 0, we toggle the LED state and reset the counter, and so that sort of generates sort of a periodic change to the LED state variable. Basically, it's toggled once per second. In the main function here, the hardware registers are configured basically to set up the timer interrupt, and then the main loop of the program just repeatedly polls the LED state variable and then either writes all ones to port 1 or writes all zeros to port 1. And basically whenever we write a 1 bit to port 1, the corresponding output pin goes high, we get a high voltage on that pin, and when we write a 0 bit, the voltage on the corresponding output pin goes low. However, because the output pins can only sink current and not source current, basically the LED will turn on when we write a 0, because that will allow current to flow from VCC through the current limiting resistor and the LED, and then into the output pin. All right, so to actually compile this C code, the makefile uses the SDCC compiler, and the target is an Intel hex file. Intel hex is basically a very simple text-based format that essentially specifies for ranges of addresses basically what specific byte values should be stored at those addresses, and essentially it's a fairly common format for compiling basically code for these early embedded systems. And essentially you can take your generated Intel hex file, and burn it into your programmable memory device, or in this case we're going to burn it into the code data storage in the flash memory of our AT89C2051 device. Okay, so basically all we have to do is type make, and then SDCC runs and produces the hex file. And then the next thing we need to do is use our device programmer to program it onto the actual device. So let's go ahead and do that. All right, so here I am in the Mini Pro software, and I've selected the correct IC type here for the AT89C2051. And basically all I need to do to get the LED blink program onto the device is load the hex file in Mini Pro. And notice I need to set file format to Intel hex so that the contents are interpreted correctly. So now we have the correct data in the Mini Pro software buffer, at which point now I can select program and then hit the program button here, and now the data is being basically burned onto the chip. So looks like it was successful. So let's see if it works in the actual circuit. All right, so here's the breadboard we're going to use for our circuit, and you can see the 16 megahertz oscillator here with the two 22 picofarad capacitors. This is the 100 nanofarad capacitor that's used to generate the initial reset pulse. And the actual IC for the microcontroller, I'm going to put in this ZIF socket, and as you can see, I've soldered some header pins onto the ZIF socket, and basically that's going to be useful to prevent the pins from breaking as we repeatedly put the microcontroller in and take it out as we sort of work on the firmware and program new firmware into it. So this is the actual device. So let's engage that, and so now we just need to apply power, so give me a moment. All right, so I've got the power leads connected, so I'm going to turn on my power supply, and there we go. So the LED is blinking. So even though this is a pretty humble little program, this is really good confirmation that the program is running, and we've basically our tool chain is working, our programmer is working. We've basically gained control of the device. All right, so here is the next application that we're going to try. I'm going to hook up a 748C595 serial to parallel shift register to 3 pins of port 3 on the AT89C2051. And shift registers are a very common way to add additional outputs or additional inputs to a microcontroller that has a limited number of pins. I don't know that I will necessarily need to use one of these for my eventual application of a keyboard controller if I use the larger 40-pin device that actually has 32 GPIO pins. But nonetheless, it's still kind of a useful step to try interfacing an arbitrary device to the GPIO pins of the microcontroller that you're learning and see if you can get it to work. So, okay, let's look at our test program. All right, so very quickly, before we look at the actual circuit for the shift register demo, let me very briefly explain how the shift register works. And so the idea is that there are 8 flip-flops arranged in a chain inside the shift register. And essentially, we can basically control the value of the first one by sending a 0 or a 1 here on pin 14, the serial input. And every time we send a low to high transition on the serial clock input here on pin 11, that basically clocks a new value into the first flip-flop, but then sends the original value of the first flip-flop to the second flip-flop, and then the second flip-flop sends its value to the third flip-flop, and so forth. So essentially the bits sort of move forward by one position every time we clock the serial clock. And so using the serial and serial clock inputs, we can generate an arbitrary bit pattern in these internal flip-flops. Then when we have all of the bit pattern values just exactly the way we want them, we send a low to high transition on the register clock, pin 12, and that makes all of the internal flip-flop values appear on these outputs. And so essentially, this gives us a way of using 3 digital outputs that we can control using microcontroller pins to generate arbitrarily 8 outputs on the shift register. So, okay, let's look at the program. All right, so here's the demo program for the shift register, and it's based on the LED blink program. And essentially, we have these 2 variables, this direction variable and this val variable. And the direction variable is either 1 or 0. And then val always has exactly 1 bit set, and its initial value is 1. And so the idea is each time the timer counter variable reaches 0, we reset it, but then we either shift val 1 position to the left or 1 position to the right, depending on the value of the direction variable. And if val has reached either the lowest bit or the highest bit, then we reverse the direction. And essentially what we'll see is that if we blink an LED based on which bit in val is set, we'll sort of get a kind of a bouncing pattern. And then the important part of the code is this SR-write function, which sends 1 byte of data to the shift register. And essentially the way it works is, given the value that is being written, we go 8 times, once for each bit of that value. We check the highest bit. Depending on whether it is a 1 or 0, we either generate a 1 or a 0 on bit 1 of P3, so that's the one that is output to the serial input of the shift register. Then we send a low to high transition on the serial clock input. That's bit 2 of port 3, which is connected to the serial clock input on the shift register. And then after all of the bits have been shifted out, we send a low to high transition on the register clock, which is bit 2 of port 3, which is then connected to the register clock input on the shift register. And then all the main function does, aside from setting up the timer interrupt, is over and over again just writes the current value of the val variable to the shift register, and essentially we'll see a pattern generated on a block of 8 LEDs that correspond exactly to the bits of this value. Okay, let's see the circuit in operation. All right, so here's our circuit, and once again, we've got the microcontroller in the ZIF socket. Here is the 748C595 shift register, and its outputs are connected to this bank of 8 LEDs. So let's turn on the power supply, and so basically, what you see is the this 1 bit that is set in that val variable appears on one of the 8 LEDs and just kind of bounces back and forth. So that's pretty cool. Basically, we can send arbitrary bit patterns to the shift register, and based on these 3 pins on port 3 from the microcontroller, and it does seem to work. So that's good. All right, so for our last experiment, I'm going to try doing both digital input and digital output. And obviously, doing both input and output is important if you have an application that requires both. So far, we've just only done output. And my input device is going to be very simple. It's just going to be a push button switch, which when pressed is going to connect port 3 pin 2 to ground, and essentially I should be able to detect whether there is a 1 or a 0 here based on whether or not this switch is pushed. Essentially pushing it should sort of overcome the internal pull-up on this input pin and connect it to ground and generate a 0. And if it's not pressed, then the internal pull-up, in theory, sort of keeps the input at 1. And then based on the status of this push button, I'm going to simply control an LED that is connected to pin 3 of port 3. And as before, we can't source current from an output pin. And so instead, when a 0 is generated here on this output pin, that will allow current to flow from VCC through a current limiting resistor through an LED into the output pin. And so writing a 0 bit to bit 3 of port 3 should cause the LED to come on. Okay, let's see if we can make this work. All right, so here is our test program for this input and output program. It's quite simple. Basically, we set all pins to a high value on port 3. My reading of the data sheet indicates that that's necessary in order to treat any pin as an input. And then in a tight loop, we check to see if the button is pressed or not. If we see a high value on bit 2, that means that the button is not pressed, and so we set a high value on the output pin, and that keeps the LED off. Otherwise, if the button is pressed, then we set a low value on pin 3, and that should turn the LED on. So essentially, whenever the button is pressed, the LED should go on. If we release the button, then the LED should go off. So let's see if this actually works. All right, so here's our demo circuit, and as you can see, we have a push button switch, and then we also have the LED. So let me turn the power supply on. So now the circuit is powered, and basically if I press the switch, that should cause the value that we read on pin 2 of port 3 to switch from 1 to 0, because the switch is going to connect the voltage at that input pin to ground. And so if I do press the button, it does happen, and the input value goes to 0, and that does turn the LED on. And so if I release the push button, essentially what we expect to happen is that the voltage at that node in the circuit will return to a high voltage because it is pulled up by the internal pull-up resistor on the I/O port, and then the firmware program should detect that and turn off the LED. So I'm going to release the push button. And so oddly, the LED stays on. And essentially what that seems to indicate is that if there is a transition on an input from 1 to 0, it doesn't seem to automatically switch from 0 back to 1 when the voltage at that node in the circuit is allowed to sort of return to a high level. So the switch is no longer connecting that node of the circuit to ground, and yet the value of that input continues to be read as a low value, and the LED stays on as controlled by the firmware program. So this is certainly kind of a weird behavior that's quite different than what I'm used to for microcontrollers such as the AVR, where basically you reliably read a 1 or a 0 on an input according to the potential that is created at that node in the circuit by whatever sensor device you've hooked up. So let's see if we can fix that. All right, so what I have done to try to work around this problem is before we attempt to read an input bit from port 3, specifically on pin 2, I am setting pin 2 to a high value, hoping that that will allow me to correctly read either a high or a low input on that input pin. Okay, so I am going to recompile the program and burn the firmware onto the device again, and let's see if that fixes the problem. All right, so here we are. I have programmed the revised firmware into the device. So let's power on the power supply. And I'm going to press the push button here, and the LED comes on. And I release, and the LED goes off. So what this seems to imply is that if you want to read a digital input value from a port on an 8051 device, you need to write a 1 to that port first, sort of eagerly. And in other words, once an input causes a port value to switch from 1 to 0, it doesn't seem to automatically get restored from 0 to 1. So that's interesting, and it's definitely a little bit different than what you might be used to if you have used AVR devices and Arduinos. All right, so this is a good place to wrap up, and essentially I will declare these experiments a success. We were able to do both digital output and digital input using the 89C2051. One thing we did note is that you need to write a 1-bit onto a port before you can actually read input from that bit of the port, but that's not a big deal. We can do that. As far as output is concerned, we also noticed that the output pins can sink current but cannot source current, and that's not such a big deal. You know, for example, if we want to drive an LED, we just connect the cathode to the output pin instead of the anode. You know, not a big deal. We can do that. The tools for 8051 development, such as SDCC, worked fine. No big deal there. I kind of appreciated the fact that we had an authentic workflow, so no libraries, no in-circuit programming. It was pretty much programming bare metal right onto the microcontroller. I like that. So what we're going to do next is when my 89C52 parts arrive, I'll do some similar experiments with those, and eventually, when we get to the keyboard controller, that will be our target device. Okay, see you in the next video.